Okay, so today we're going to be going through some A-level Edexcel maths proof questions. Now these may be taken from paper 1 or paper 2 or maybe some mock exam questions from previous years. And if at any point you have any questions, then feel free to put them in the comments and I'll try to answer them as quick as I can. So the first question we have is use proof by exhaustion to show that for every natural number n and n is less than or equal to 4, so in other words all numbers from n equals 1 up to 4, so just the numbers 1, 2, 3, 4, we want to show this holds. Okay, so for this is nice and simple. We just need to put in n equals 1, n equals 2, all the way up to n equals 4 and show that this holds. So for n equals 1 on the LHS, so on the left hand side, what do we get? So we get 1 plus 1, which is 2, and then 2 cubed, which is 8. And on the RHS, so on the right hand side, we get 3 to the power of 1, which is just 3. Okay, similarly for n equals 2 on the left hand side, we're going to get 2 plus 1, which is 3, and then 3 cubed, which is 27. On the right hand side, we get 3 squared, which is 9. And indeed 27 is bigger than 9 and 8 is bigger than 3. Let's do this now for n equals 3. So on the left hand side, we'll get 3 plus 1, which is 4. 4 cubed is 64. And on the right hand side, we get 3 to the power of 3, which is 27. So then 64 is indeed bigger than 27. And then finally for n equals 4, on the left hand side, we get 4 plus 1, which is 5. So 5 cubed, 5 cubed is 125. On the right hand side, we get 3 to the power of 4, which is 81, and indeed 125 is bigger than 81. So that proves by exhaustion that n plus 1 cubed is bigger than 3 to the n for n natural less than or equal to 4. Okay, now for part 2. Given that m cubed plus 5 is odd, use proof by contradiction to show that m is even. Okay, so proof by contradiction, that means we want to assume the opposite. Okay, so we assume that m is odd. Okay, so we assume m can be written like this. Okay, so we're assuming m is odd. Okay, and if we assume m is odd, then m cubed we can write as 2n plus 1 all cubed. Okay, now this is just a binomial expansion, so we get 8n cubed plus 3 times 2n squared times 1 plus 3 times 2n times 1 squared plus 1 cubed, so just 1. Okay, now just simplifying this, so 8n cubed plus, well, 4n squared times 3, so 12n squared. 3 times 2n, so 6n plus 1. Okay, so we're almost done. Now we just need to arrive at our contradiction. So we're going to factor out a 2 from just the first 3 terms, and we get 4n cubed plus 6n squared plus 3n. So why have we done this? Well, we were given that m cubed plus 5 is odd. Okay, so now what we're going to do is we're going to write m cubed plus 5. So m cubed plus 5 is going to be all of this stuff. So 4n cubed plus 6n squared plus 3n and then plus the 1, and then plus the 5, so plus 6. Okay, so this is m cubed plus 5. Now we were given that m cubed plus 5 is odd, but this is clearly an even number, okay? Because this is the sum of 6, which is even. So it's the sum of 6, which is an even number, and 2 times another number. So this number is even, and 6 is even, so therefore this is even, which is a contradiction. Which is a contradiction. And therefore our assumption that m is odd has to be false, so therefore m has to be even. Okay, so that's part 2 done. And now if you wanted to, you could then factor out another 2 from the 6 as well. So then you would get something like, then you would just end up with something like that. And then that also shows that the final number is 2 times something, which is even. Okay, now the next question we want to do is we want to disprove that if m and n are irrational numbers, where m is different to n, then mn is also irrational. Okay, so we want to disprove this by a counterexample. There's a couple you can think of. Now m we can set to be root 2. That's probably the simplest irrational number that we can think of. And now we want to choose n, so that when we do m times n, we get a rational number. So if we chose, obviously if we chose n is equal to root 2 as well, then mn it would be 2, which is rational, but this doesn't work because we need m to be not equal to n. So the simplest thing to do here is to just change this into a minus root 2, so then mn will be minus 2. Okay, and minus 2 is rational, and therefore this statement has been disproven. Okay, now part B, we want to sketch the graph of y is equal to mod x plus 3. So the graph of mod x is just the sort of V shape, and we want to shift it upwards by 3. So we're gonna take the normal modulus graph and we're gonna shift it upwards by 3. So it will look something like this with y-intercept 3. Okay, now part 2, explain why mod x plus 3 is bigger than or equal to the modulus of x plus 3. So why is this bigger than this? Now part 1 has hinted at sketching graphs, so we're gonna sketch the graph of this as well, modulus of x plus 3. So sketching that in a different color. Well, x plus 3, the normal graph of that looks like this blue line, okay? Taking modulus, basically all of this part, all of this negative part will be reflected upwards, right? So this part of the blue line will stay the same, but this part will reflect upwards and will look like that. Now part 2 is asking why is basically the this black line, the graph represented by the black line, bigger than or equal to the graph represented by the blue line. And from here you can sort of just describe what you're seeing. So for x, for values of x bigger than or equal to 0, the graphs overlap, so therefore they're equal there. So in other words, for x is bigger than or equal to 0, we have that mod x plus 3 is actually equal to mod x plus 3, like this. But for values of x less than 0, what's happening? Modulus of x, so mod x plus 3 is just strictly bigger than the other one, mod x plus 3. So therefore, overall we have a weak inequality, bigger than or equal to. Okay, so for this question, we want to show that the derivative of cos theta is minus sine theta. And we want to show this from first principles. Right, so if we want to do it from first principles, then we need to choose a small value of h, and we need to work out the gradient between theta and theta plus h. Okay, now the gradient is just, of course, the change in y. So the change in y will be cos theta plus h minus cos theta. So that's the change in y, and we want to divide it by the change in x, which is just our little h that we added on. Okay, now from here we're going to use the hint, which is you may assume the formula for cosine of a plus or minus b. So cosine of theta plus h is just cos theta cos h minus sine theta sine h, and we still have the minus cos theta on the top, all over h. Okay, now we're going to use the other two hints. So sine h over h goes to 1, and cos h minus 1 over h goes to 0, as h goes to 0. Okay, so for that we're just going to sort of factor out on the top. We're going to factor out the cos theta between the first and from the first and last term. So we get cos theta cos h minus 1 all over h, and we're also splitting up the fraction in one go. So then we get minus sine theta sine h over h. Okay, so that's our expression, and now to actually take the derivative we need to send h to 0. So send h to 0 to get, well, what do we get? So sending h to 0, this we're told goes to 1, that goes to 1, and this thing here, cos of h minus 1 all over h, well, that goes to 0. Okay, so the first term disappears. Okay, so this whole term, this first term just disappears. This becomes 1 basically, so what we're left with is just sine theta times 1. Okay, so here we're just left with sine theta times 1, but remember we've got the minus sign here. So send h to 0 to get minus sine theta. Okay, so for question 2, we want to show that for all natural numbers n, so in other words for all whole numbers bigger than or equal to 1, that n squared plus 2 is not divisible by 4. Okay, so for these type of questions it's useful to consider a contradiction argument. So we're going to assume that for every whole number bigger than or equal to 1, that n squared plus 2 is divisible by 4 for every natural number n, and this is our assumption for a contradiction. So we assume this is the case. So if this is the case, then we can write n squared plus 2 is equal to some number times 4, where this number is just some natural number. So n squared plus 2 is 4 times m, where m is some natural number. Okay, just rearranging this, we get n squared is equal to 4m minus 2. Let's factor out the 2, so we get 2 times 2m minus 1. So what we have now shown basically is that for every natural number n, that the square of n is even, because it's 2 times some whole number. But we know that this is not the case, because if we take just, for example, n is equal to 3, then n squared is equal to 9, and 9 is not an even number. So therefore our assumption is false, and therefore we've proven our original statement. Okay, now part 2. So given a real number x, the value of mod 3x minus 28 is greater than or equal to the value of x minus 9, always, sometimes, or never. And we need to determine which one of those three is the case. So with this, it will be useful to sketch the graphs of mod 3x minus 8 and of x minus 9. So for 3x minus 8, well, without the modulus, it would look something like that, okay? And it would intersect the x-axis at 28 over 3. But we have the modulus, so basically the negative part will all be reflected upwards like that. So this part of the graph won't exist. So let me just redraw that. So we're going to have some sort of graph like that. Okay, now for the other graph, x minus 9. Okay, now that is going to intersect the x-axis when x is equal to 9. Okay, so first of all, 28 over 3. So 28 over 3 is 9 and 1/3, okay? So 9 will be just around there. Now, the key thing here is that the graph, this graph is going to be less steep, okay? Because the gradient is only 1. So the gradient of x minus 9 is only 1, whereas the gradient of this line is 3. So therefore the line will be something like this, and you can see that the graphs intersect at 2 points, okay, at this red point, at these 2 red points. So this is only sometimes bigger than x minus 9, okay? So if we find these intersection points, then we can say what values of x it's bigger than and what values of x it's smaller than x minus 9. So clearly between these two red dots is this value, 28 over 3. So if we substituted 28 over 3 into here, then we'll get 3 times 28 over 3 minus 28. In modulus, that is just a 0, but 28 over 3 minus 9 is a third, okay? And 0 is less than a third, okay? So at that point, this is less than this. But other points, for example, let's take just a large number, or let's take 0, okay? Let's take x equal to 0. So at x equals 0, our first one will become 3 times 0 minus 3 times 0 and then minus 28, and then modulus in that is 28. But the other graph at x equals 0 is 0 minus 9, which is minus 9. So then 28 is bigger than minus 9. So we've shown that at some points this is greater than that, and other points it's smaller. Okay, now the last one we're going to cover today is this. Prove by contradiction that there's no positive integers p and q such that 4p squared minus q squared is 25. Okay, first of all, this screams difference of two squares. So we're going to factorize this using difference of two squares. So we get 2p plus q, and then 2p minus q is 25. Okay, now 25, what are the factors of 25? So we have 1, 5, 25. These are the positive factors. Okay, but there's nothing stopping these things from being negative as well. So we can have plus or minus 1, we can have plus or minus 5, and we can have plus or minus 25. So now let's suppose 2p plus q was equal to 1, then in that case 2p minus q would have to be 25. Okay, so that's case 1. And solving these simultaneously, well, we can add them up. You get 4p is equal to 25, and p, in this case 25 over 4, is not an integer. Is not an integer. So therefore it's not a positive integer. So p is 1 and q is 25 does not work. Okay, so now let's try. 2p plus q equals 1 and 2p minus q equals 25 doesn't work. So now let's try 2p plus q equals 5. 2p plus q equals 5. So therefore 2p minus q equals 5. Solving the same way again, we get 4p is equal to 10. And again, clearly p is 2.5, which is not a integer. So this also doesn't work. Now let's try 2p plus q equals 25. So then 2p minus q is equal to 1. And this will give the same case as the first. So 4p is equal to 25, and that we know does not work. So the other cases we can consider are 2p plus q is equal to minus 1. So then 2p minus q is equal to minus 25. And in this case, adding them up will give 4p is equal to minus 26. And clearly p is equal to minus 26 over 4 is not a positive integer. Two more cases left, so 2p plus q is equal to minus 5, and 2p minus q is also equal to minus 5. Adding them up gives 4p is equal to minus 10. So p is equal to minus 2.5, which is again not a positive integer. And the final case we have to consider is 2p plus q is equal to minus 25. 2p minus q is equal to minus 1. And this boils down to this case again. So we'll end up with 4p is equal to minus 26. So p is not a positive integer. Okay, so that will wrap up today's video. I hope you did find it helpful. Now, again, if you do have any questions, then feel free to drop them in the comments below, and I'll try to answer them as soon as I can. Now, I also do offer private tutoring services up to A-level maths. So whether it's SATs, 11+, GCSE, or A-level maths or further maths, and whether you need help with your pure mechanics or stats, I am more than happy to help. And if you do have any inquiries about that, then feel free to drop them in the comments below, and again, we can arrange something. Or you can have a look at my website, tutor.rvmukesh.com, and you can contact me through there. Other than that, if you do have any requests for future topics you'd like me to cover, or any past papers you want me to go through, then again, feel free to drop them in the comments below, and I'll try to accommodate for them in a future video. Other than that, good luck and take care. I'll see you in the next one.